Hello and welcome back to the deep dive. Today we are going to visualize something properly. I want you to just close your eyes for a second.
Okay.
Imagine you are in the chemistry lab. You're holding a test tube. Inside, there's a clear, colorless liquid. It looks just like water, but it has that sharp smell like nail polish remover. That's acetone.
Which is a standard ketone. You'll find it in every single school lab.
Exactly. Now imagine you take a dropper and you add a few drops of a specific chemical called Brady's reagent.
And for the students making notes, that's a solution of 2,4,4-dinitrophenylhydrazine, or just 2,4-DNP for short.
That is a mouthful. So you add this 2,4-DNP. And the moment that drop hits the liquid boom, immediately, out of nowhere, a bright orange or maybe a red solid appears.
The precipitate, yes.
Just clouds up the whole test tube. It's a really dramatic color change. You might ask, is it magic?
No, it's not magic. It is chemistry, and it is exactly the type of reaction we are covering today.
It's a fascinating reaction.
It is. And you are right, not magic, but a very specific mechanism. Today, our mission is to master the chemical reactions of aldehydes and ketones.
Which is the heart of Unit 8, aldehydes, ketones, and carboxylic acids.
Yes.
And this is a heavy unit for Class 12 students, I think. Many students find organic chemistry a bit difficult here.
It is challenging, but, understanding this specific reaction mechanism is the key. It's not just about making orange powders in the lab. If you understand what we discussed today, you can predict how these compounds behave, how we make medicines, and crucially for our listeners, how to solve those tricky complete the reaction questions in your board exams.
That is exactly what we want to hear. We want to secure those marks. So let's unpack this. We have this Unit 8. What is the core idea here? At the simplest level, why do they react the way they do?
Okay, so at the simplest level, aldehydes and ketones react because of one specific feature, the CO bond.
The double bond.
Yes, we call this the carbonyl group. And the main reaction they undergo, if you remember nothing else from today, remember this, is nucleophilic addition.
Nucleophilic addition. Okay, let's break that down, because I know in exams, students, they sometimes get confused. They hear addition, and they think of alkenes.
Yes.
Which also have double bonds.
Correct.
Yeah.
And that is the biggest strap. But let's look at the structure first to understand why. You have a carbon double bonded to an oxygen. Now imagine that bond, it can break. And a nucleophile, which is basically an electron-rich species, it attacks the carbon.
So the bond breaks, and something just sticks to the carbon.
Precisely.
I want to help our listener visualize this. You said imagine. Let's do that properly. Listener, if you can, just close your eyes again.
Yes. Imagine the carbon atom in that CO bond.
Yeah.
Now, carbon and oxygen are sharing electrons, but they are not sharing equally. Oxygen is very greedy.
Okay.
It's highly electronegative, so it pulls the electron cloud towards itself.
The oxygen is feeling a bit negative.
Yes, slightly negative. We say delta minus. And that leaves the carbon feeling slightly positive, or delta plus. It is electron deficient.
Right.
Now imagine that positive carbon acting like a magnet.
A magnet. That's a great image.
It is. It's a magnet for nucleophiles. Nucleophiles have extra electrons. They are negative. So just imagine the electrons from a nucleophile being attracted to that carbon magnet. As the nucleophile gets closer, it attacks.
But what happens to the double bond when it attacks?
The double bond, the pi electrons, it gets pushed away, it just snaps open like a gate, and the electrons, they flow onto the oxygen. So the result is the oxygen becomes fully negative, and the nucleophile is now stuck to the carbon.
That's a very clear picture. So the carbon was positive, the nucleophile was negative, they attract, and the oxygen takes all the extra electrons.
That is what is really happening at the particle level. It is all about polarity. The carbonyl group is polar. Carbon is slightly positive, oxygen is slightly negative. The nucleophile attacks the positive carbon, but the reaction isn't finished yet.
Right, because we have a negative oxygen now. It can't just stay like that.
Exactly. So in the second step, a proton, usually H+ from the solution, it comes along and adds to that negative oxygen to finish the job.
So it's a two-step dance. Step 1, attack the carbon.
Yes.
Step 2, protonate the oxygen.
Perfect. And if you need the Anger definition, the one you write in the exam for full marks, it is this. Aldehydes and ketones undergo nucleophilic addition reactions at the CO group due to the polarity and electrophilicity of the carbonyl carbon.
Electrophilicity of the carbonyl carbon. That's a heavy phrase. Can we simplify? Electrophilicity?
It just means the carbon loves electrons. Iono means loving. So it is electron-loving. It is seeking them out because the oxygen is pulling them away. It's hungry for electrons.
Okay, I have to stop you there because you mentioned a trap earlier. You said students confuse this with alkenes. I want to make sure we fix this misunderstanding right now.
Yes, absolutely. This is a classic misunderstanding trigger line.
Yeah.
Students see a double bond in CO and they think, oh, CC double bonds and alkenes do electrophilic addition, so this must be the same.
But it's not.
It is the complete opposite. Alkanes do electrophilic addition, carbonyls, aldehydes, and ketones do nucleophilic addition.
And the reason is that polarity we just talked about.
Exactly. In an alkene, CC, the electrons are shared equally. It's nonpolar. The double bond itself is a big cloud of electrons, so it attracts positive things, electrophiles.
Okay, but in CO?
In CO, that polarity makes the carbon positive. It acts like a positive magnet. So it invites the nucleophile, which is negative. If you get this wrong, you lose marks. It's a fundamental error.
Okay, let's put it on a bumper sticker. CO invites nucleophiles. CEC invites electrophiles. That is a clear distinction. Let's go back to that magnet idea. I really like that analogy.
It's the primary analogy for this topic, I feel. Think of the carbonyl group like a magnet with some iron filings.
Okay, so the carbon atom, the delta plus 1, that's the north pole of the magnet.
Correct, and the nucleophiles. They are the iron filings.
So just like in physics class, the filings will fly towards and stick to the magnet.
Exactly. The nucleophiles fly towards and stick to the carbon. And once they are attached, they become part of the new product. They don't just sit there, they form a proper bond.
Why does this concept even exist? I mean, why do we care so much about this sticking process?
Because without understanding this mechanism, we simply cannot synthesize new products. This is how chemists build the world. Think about Grignard reagents.
Oh, Grignard reagents. That is a scary name for some students. RMGX.
It shouldn't be. It's just a tool, a very powerful tool. It's how we add carbon chains. This mechanism allows chemists to build complex molecules like pharmaceuticals. It basically solves the problem of how do we predict what happens when we mix these chemicals? If you know the magnet analogy, you can predict the result.
Let's run a mental movie. I want to really see this happening in slow motion. Let's visualize cyanide, CN, attacking an aldehyde. This is a standard exam reaction, isn't it?
Yes, the reaction with HCN to form cyanohydrins. Very, very common in board papers.
Okay, listener, back to the mental movie theater. Scene. An aldehyde molecule, say RCHO, is floating in space.
Picture that CO bond glowing. The carbon is glowing with a soft positive light. The oxygen has a soft negative light.
Action. A cyanide ion, CN, enters the frame. It looks aggressive. It has a lone pair of electrons ready to go.
It is looking for that positive charge. It is looking for the magnet.
Attack. The CN zooms in and hits the carbon. Bam.
And immediately, the break, the double bond, the pi bond, it just snaps open. Imagine the electrons flowing like water away from the carbon and onto the oxygen.
So now the oxygen is glowing brightly negative. It holds all the electrons.
The finish. A proton, H plus E, floats by. It sees that negative oxygen and attaches to it.
And the end product.
A cyanohydrin. It is neutral, stable, and you have successfully added a carbon atom from the cyanide to your chain.
That is beautiful. The electrons flow like water onto the oxygen. That image really helps.
It is very intuitive once you see the polarity. And remember, the carbon also changes shape. It goes from being flat, trigonal planar, to being tetrahedral. It sort of puffs out.
That is a great detail. Now let's talk about some real-world examples. We started with that orange test tube, Brady's reagent.
Yes, that is the observable phenomenon. The chemical name is 2,4-DANP.
And this is a standard lab test, correct?
Yes. If you are given an unknown liquid in a practical exam and asked, is this an aldehyde or ketone, you use this. The chemistry is exactly what we just described. The hydrazine part of the molecule, that is the nucleophile, it attacks the acetone carbon.
And it forms that bright orange solid.
It forms a seal and bond, and it releases a water molecule. The bright orange color proves that the new double bond has formed. It's a dead giveaway.
I want to go back to that scary reagent we mentioned, the Grignard reagent, RMGX. You called it a super tool.
It is a super tool in organic synthesis, no doubt.
Why?
Because it creates new carbon bonds. That is actually very hard to do. Usually we just change functional groups from one to another, but Grignard lets us make the whole carbon skeleton bigger.
So how does the mechanism work here? Is it the magnet again?
It is the same story, just a different character.
Right.
In Grignard reagent, RMGX, the magnesium is a metal, so it is positive. That forces the carbon group, the R group, to be negative.
A negative carbon. That sounds very unstable.
It is very unstable, and that is why it reacts so fast. This negative carbon, it acts as the nucleophile. It attacks the carbonyl carbon magnet.
And the result?
After you add some acid water, that is the second step, you get an alcohol.
Okay, so Grignard plus carbonyl equals alcohol.
Yes, and it matters because it's how we make alcohols with new carbon chains attached. If you see a conversion question in your exam where the carbon chain gets longer and ends up as an alcohol, you should immediately think Grignard.
That is a golden tip.
Mm.
Long chain alcohol. Think Grignard. Now, we touched on this, but let's hit the counterintuitive example again. The student thinks double bond equals electrophilic addition.
Right. Both have double bonds, so shouldn't they react the same way? It's a logical question.
And the correction is?
No, CC is nonpolar. CO is polar. Oxygen is greedy. So because of this, CO invites nucleophiles, and CAC invites electrophiles.
Getting this wrong is a major reason for losing marks.
It's fundamental. If you write electrophilic addition for an aldehyde, the examiner just stops reading.
Ouch. Okay, listener, do not do that. We are going to move into our exam-safe clarity lines. These are the sentences you need to have locked in your brain. So what's the first one?
Clarity check 1, and this is very important. Aldehydes are more reactive than ketones towards nucleophilic addition.
Wait, hold on. Why? Both have the COO bond. Why are aldehydes faster?
There are 2 reasons, and you need to rate both for full marks. First is steric hindrance.
What does that mean in simple English?
It just means crowding. Think of the aldehyde carbon. It is attached to one hydrogen and one R group. It's relatively open. The door is open for the nucleophile to come and attack.
And the ketone?
The ketone carbon is attached to 2 bulky R groups. Imagine 2 big bouncers standing in front of the door.
Right.
It's crowded. The nucleophile has a much harder time getting in, so aldehydes react faster because they are less crowded.
Got it. Aldehydes are less crowded, so they are more reactive. What is the second reason?
The electronic reason. We said the carbon is positive, right? Yes, the magnet. Now, alkyl groups, these R groups, they have a tendency to push electrons. They are electron donating.
Okay.
In a ketone, you have 2 R groups pushing electrons onto the carbon. This reduces the positive charge.
It makes the magnet weaker.
Exactly. A weaker magnet attracts the nucleophile less. An aldehyde only has 1 R group pushing, so its magnet stays stronger.
Crystal clear.
Okay.
Clarity check number 2.
Nucleophilic addition is a 2-step process.
We saw this in the mental movie.
Yes.
Yeah.
Step 1, nucleophile attacks carbon. Step 2, proton adds to oxygen. Don't merge them into one mess when you are writing the mechanism. Keep them distinct.
Clarity check 3. This one is about oxidation.
Correct. Aldehydes are easily oxidized to carboxylic acids. Ketones are resistant.
This is useful for distinguishing tests, right? Like Tolman's test.
Exactly. Toland's test, Feeling's test. These work on aldehydes because aldehydes are easy to oxidize. They don't work on ketones because ketones are very stubborn. They resist oxidation.
That's because the aldehyde has that lonely hydrogen attached to the carbonyl, isn't it? It's ready to go.
That hydrogen makes all the difference. Breaking a CH bond is much easier than breaking a CC bond in a ketone.
And clarity check 4. We mentioned water leaving earlier.
Yes. Condensation with ammonia derivatives involves nucleophilic addition followed by the loss of water.
So this is like the Brady's reagent reaction we started with.
Correct. It explains the formation of things like immunes and oximes. First it adds, then a water molecule drops out.
So if you see ammonia derivative, you should look for the water molecule leaving.
That is the trick. Remove the oxygen from the carbonyl, remove 2 hydrogens from the nitrogen, join them up. Simple.
This has been a very, very productive session. We've covered the mechanism, the analogies, the examples, and the exam tips. Let's just bring it all together in a short summary.
Yes, a quick recap for revision.
Point 1, the core idea. It is all about nucleophilic addition. And why? Because of that polar CO bond.
Correct. Carbon is positive, delta plus, oxygen is negative, delta minus.
Point 2, the analogy. The carbon acts like a magnet for nucleophiles.
And the filings, the nucleophiles, fly to the magnet, the carbon.
Point 3, the examples. We saw Brady's reagent turning orange. That's the visual anchor. And Grignard reagents making alcohols with longer chains.
And point 4, the most important exam tip. Remember, aldehydes react faster than ketones. And the 2 reasons are steric hindrance, or crowding, and the electronic reasons, meaning the weaker magnet in ketones.
And please do not confuse it with alkanes.
Never. Alkanes do electrophilic addition, carbonyls do nucleophilic addition.
Now, before we sign off, we always like to leave you with a little something to think about. A provocative thought.
Yes. We talked a lot about how aldehydes are easy to oxidize and ketones are resistant. We said ketones are stubborn.
Right. They don't react with mild oxidizing agents like Toland's reagent.
Well, what happens if you try to oxidize a ketone very harshly? If you use a very strong oxidizing agent like concentrated nitric acid in high temperature, does the molecule survive or does it break apart completely?
Oh, does it snap?
It does. It snaps the carbon-carbon bond next to the carbonyl group. It is a very violent reaction compared to the elegant addition we talked about. And there is actually a rule about where it breaks. It's called Popoff's rule.
Popoff's rule. That sounds important for competitive exams.
It is. So I want you to open your textbook and look for oxidation of ketones and Popoff's rule. See if you can figure out which side of the molecule breaks.
That sounds intense. So listener, go check that out. And next time you see a complete the reaction question, don't panic.
Okay.
Close your eyes. See the magnet, see the filings, and let the nucleophile attack.
It is all about the mechanism.
Thanks for listening to The Deep Dive. Good luck with your studies.
All the best.